based content. So I had no idea how to tune it up. It was never something actually that in bullets. Really started figures out in those in games consoles, got like game ranges and linkers to different. With Flutter, we don't really have access to GPU and let's do that kind of try and match one. So we might do something else if I'm contending. Now, there is a project called Flutter GD that will imply but really sure for this until you get whacked away so long. So what I'm talking to say is a way to set up your own free frame that will start from scratch. It starts at the there's no GPU goes, has the edge point is just a Flutter custom edge present with a canvas element, multiple lines on that, which we can see. So there's no GPU complexity, it's all on the offside. Now, we're going to use the lines of our primitives to set of triangles. So we kind of do it in a different vibe and machine semi protect. But other than that, this full 3D, we'd have a 3D environment and we're just meant to do that and just sort of cut it to the 3D projection, just like the way that we've done in triangle window. Okay. Right, so what's the motivation? My animal line, but I was really up into group up in your way of arc and just getting knowing. So like Space Invaders and then we had asteroids, which is kind of like place the child for effect game. So in the old days, the resolution space sort of folk and more CRT did the thing cabinet, but Space Invaders till we can't the 78 because I can go 224 environment 216, quite a little resolution. Then the design of the asteroid saying it's not enough for us to make this game and help the player be able to pack of the shoes that the gas list source and so on in the game. So they trace a little bit, split down as target. Now we know that there is vector displays we can unlock that pixel one again. We then always use raster grids and fat common displays, and this is a shame because that's sort of if you ever see a like Astral Age cabinet or like a certain terminals, then you know those games. There's quite a different look, which is really nice to enter the unmasked displays in the core wants to stay. So got me thinking, in another universe, what happens if vector displays were actually self-taught? How will we use them today? Where we now have much more power CPUs. So asteroids ran on a 650 with 8 bits. Didn't mean to have all the multiplication and you had to do all that in code, let's say. But now it is these monster CPUs to do these 31 calculations every frame. For displaying fuller, we don't have a back display for the leash, called displays and then I meant that's still 5. And we're plus as a fancy thing and transducers and get a really nice anterior spine that looks full intensity up to the fact that back to my default and really sites. Plus we can do something where in make our games a little bit like those all getting but supercharged with modern hardware much more sophisticated 3D and do all the calculations and frame remain all this. Okay. This is Carnesian 79. Asteroids. Fantastic game. It's very good chance to play the little thing on it. So we're going to look at a different version. So kind of change it up a bit. Sports have to buffer out boundaries. You've now changed that in more of a so you'll combine your play a spaceship under fire with an ounce in the lower space. And we've got completely out asteroids and resources your bodies in orbit. Speed fund. It's like I said, all running in that Flutter, that canvas elements. It's just drawing 2-dimensional lines on the spec. What we're going to do is talk through how we get this 3-dimensional projection from an environment in property 3D coordinates and I've got the details of spaceships and that's going to solve. Now, look at all here. We need to talk a little bit about maths. Most of it is hidden. It had a really nice library, vector math library. So we do talk a little bit about it. Generally just use the old data that you just don't have to understand too much how that works. We'll just need to go through that. In order to go from data that is 3-dimensional environment, fully 3D environment, world, into a two-dimensional picture on screen. Those are reflecting constellations. Based on our classical operating machines of like walls, shadable, coordinations for our base and draw and fit that. I think it's seen become a midpoint. And we need to shades count all that is in data structures in JAWS. So kind of classes you need to use to represent the base. And finally, scenes look a lot more realistic. You can change high surfaces to within the scene. So with a line-rendered vector guy in 3 dimensions, you get things like cubes where if you don't hide the back surface, you can't tell the orientation with the cube. They're negative cube illusion. We see that in the fact where a cube would have one true orientation and not how the lining seems in. They should be able to assume surfaces come looking on it when the memory syncs. So we have a look at how they're doing themselves and by the thing. The outcome in do 2 inches. Okay, it's quickly versus the maths. A vector could represent a coordinate in 2 or 3 dimensions, or it could represent any directions, just that are listed 2 or 3 numbers. The idea of the unit vector means that the modulus, the length of vector, these more units, whatever direction it's pointing. And just a couple of tools about multiplying 2 vectors together. There's 2 ways to do it. You have a dot product, which gives you a scale value, float. It tells you the angle to each vectors, and also the cosine angle to 2 vectors. So it's 2 vectors of 90 degrees, dot product, we result in 0. The mass library can only use the digit that dot on the sheet, so you don't have to write it so. Same with the cross product. Although in 3 dimensions, if you take cross product of 2 vectors, you get a vector that's perpendicular, so it's suitably used up. So in our coordinate system, our 3D model, it recorded like handed. So you have, for example, point sign is the x-axis, my forefinger, the y-axis. So that would be like any normal 2-dimensional display. Then the z-axis is coming out towards the viewer. It's y-handed system. Now, lots of graphical liners use this convention. Flutter the same, and Flutter be the same, but gel. They all feel well like this, so something to bear in mind. Matrices. Now, in order to get a coordinate from the 3D world into a 2-dimensional space, we apply a transformation matrix. And you don't need to know the details, but you do need to know that the matrix has to have the same rank and same size as the vector even multiplied by. So we will only matrix, for example, view a perspective transformation. Got the cycle you used, the math cycle you're going to use, in that way useful. It don't tell me how it works, but just until to understand the matrices. If you have transformation of representative file matrix, you can multiply those 2 matrices together, give you a transformation that applies the result of both. So let's say I make a matrix to a rotation, I make a matrix to do a translation. I multiply this together, I get a matrix that does rotation first, then translation. So I'm good matrices to reduce number of calculations and do on the coordinates and more commonly we'll apply transformation matrix to a vector. So that vector will be a coordinate in 3-dimensional space, and you can move that around, or you can upturn it in 2-dimensional coordinate by counting like integers. Just have a look at the no, lastly, if we want to represent a rotation in 3-dimensional space, we can use a matrix, but we generally don't, because the rotation matrices tends to be numeric. And you say, you start multiplying lot together, and if you render the some leading equation matrix, you will see those up and that's the income. So a quaternion is a array of 4 bobbins that represent 3-dimensional rotation. Somehow, I have no idea how they work, and then depend what it was, notice how they work. But to give you an example, let's say we take the y-axis and we rotate by max degrees, so we feel in rate in taking this month like this, so 5 by 2, because month begins quadrators can be to rotate by 90 degrees around the y-axis. But turning this 0 and 1 root 2, 0 then we need to I don't know if looking at that, you'd be able to tell what it was minus 2 rotation under. So we could just use the library hides all of these cell blocks so that it's worked up on. This is just where you get the library from on-prem dev. It's called Vector Math, Amazon project. I like to use in 64-bit version because I can double this, but there's a third question. But unfortunately, there's an colors object which will cache with more than two little colors objects at that insane BIOS, a commonly unified colors object image. This provides the vectors, matrices, and terminals that we want to talk about. And also some complements to make matrices you need for 3D vector transformations, like vector matrices and then the closing space. Okay, back to our world quality system. Remember, we were saying it's right-handed. I suppose you call it English, and of course, quantum is called, but quantum is called, but maybe. We know that we need X, Y, and Z coordinates for the same point in space, but it tells us how to make the maths work. You actually need to know about it in multiple docking. In almost all cases, probably use one. So you have you need X, Y, Z coordinates for like one. If you accidentally enroll arithmetic deal with vectors, change that one to some really one, then the rest of calculation doesn't affect your articles, couldn't be one to make you show each way strong. Other than that, as long as you that's what we're using, all good. Okay, so we're starting off with data in our Morse's coordinate system, a spite that we're going to find, say a model layout at its local origin, which initially the origin of the world. If you think about that player station in the game, we need to move that in the origin to where it's going to go. And then we need to figure out how to display what camera thing and no other in 2 dimensions. So there are 4 steps to transform the coordinates in the world into coordinates on 2-dimensional screen, and any for in the Flutter comes with. Yeah, comes on it. So let's start looking at those. Modeling transformations are all about moving raw sprites or elements that we're using per day to where it will be in the world. So this is all happening in 3 dimensions, and typically what you'll do is you will get into a sprite direction and then we'll translate it to where it needs to go. So we can use like returning. If we imagine how to be flexible that is part of our sprite, and we want to basically use turning queue to turn this into the repetition for our to go into the right place as well our day. We know how that axis vector was our 3 vector. Let's say my y-axis 0, 1, 0. Set the values to the x, y, and z on the axis, and then you can use queues turn and set axis angle function. We can use that vector as an axis, and then do the angle radians to rotate the molecular turning the rotation on that axis. So here, if I use pi radians, 180 degrees, and make it turn in and apply to my wire to rotate it around on those games up down the axis. I think overall, a lot of it's all right, so using the right direction. You put a lot of movement to the right place in the C, and it's just a simple translation. You just patch your X, Y, and Z value, and then where you used to go. Can catch you out if you use the math libraries for a related plus operator, because firstly, if you have in your effectively add if you have a 1 in the dominant value in the same length, have the more effective move, and you're going to end up with 2, which will cause the coordinates to be bottled when you transform the virtual. Sometimes I've just spent hours to direct the embats, realize I'm not extended tagging by 1 to my W vector, it's gone on. I've done the left or not. The other thing is if you're a bit fussy about performance, the overloaded plus, that's a function call, and it also primings the input vector. So it makes a second vector, it does a memory allocation with 4 floating point dimensions, and after it's going to be created the same way as well. There's a formula saying that it was in plus. I tend to just add the individual values themselves between 2 vectors. Then no allocation and no function calls that minus those things out. Right. In that game I just showed you, you have a player ship that is orbiting the planetoid in the game. So always going to stay tangentially to the surface. And as it rotates around, it's going to rotate so it stays that way. It's also the outline is fixed. The outline, everything in the game is fixed. So they always say, let's say, when you choose what happens, worry about recent was what you managed to make. let's have a look at how we might translate the player ship from its position of the origin, which was where it comes out box from the bile, the sun icon, say it's pointing down the x-axis, some southern origin, through facts of where it needs to go in the scene. What we're going to do is we're going to make the new basis. So it 3 vectors will represent the orientation on the model with this new rotation. We can create the vertical vector, the up vector, by creating a vector from the center of the planet up to the positioning station, position will be planet. And that'll give us something direction, and it will be perpendicular to the surfacing planet, and we use that vector well efficient. If we have a forward vector, the same where it's pointing, then we can cross that to a cross product of that of up vector and then get a y vector. So that gives us a 2 of the 2 vectors, say we're in orientation, but player ship, and then cross those 2 together and we get a forward vector that is guaranteed to be tangential to the surface of the planet. So we've got kind of like an X, Y, and Z that is rotated at the right angle to rotate our plane to get it into the right orientation of the planet. Now, here's a hack. You can go from one basis to another base. That is, you can go from one set of X, Y, and Z coordinates, say you're well established, to an arbitrary rotation if you have the 3 vectors that you want to rotate to in your original basis. So what we've just calculated, the up, lines, and forward vectors, we will make a 3-by-3 matrix using those vectors as columns in your transformation vectors. Multiply that out by your original coordinates you are being get from the modeling path, your plane. So the center of the origin facing, say, down the x-axis. And that will measure rotation, will give you the right orientation. So up pressure, it matches the up vectoring the basis and make forward and right for the same. So that's how we do transformation to get her player's ship into the right orientation in the surface. And then we know where the center of the ship is. We can just do a translation and take that for the set of coordinates on the right face of the surface. Sound a bit fiddly, but it's the fastest way to get thinking, something like that. And this idea of transforming between 2 bases is so powerful for that be able to get the models the right orientation. Okay, so that was the modeling. That's all working in 3-dimensional space. You're taking your sprites and putting them where you want them, but it's all still in 3D. So what we're on now is transformation that lets us put a camera up somewhere in the sea and give us a view of the scene from that point. Now, what we're going to discuss here is common to a lot of graphical languages, gel, like you call it other stuff. You basically say the camera is going to be in a certain position, it's going to be looking at a certain way in the scene, and we have an up vector so that we get the rotation on the camera's axis. But what's really happening, what we call the set view matrix function, is that it's creating a inverse camera matrix that moves the world to where to behind the camera. So camera is always, remember we had X, Y, and Z in our world. The camera is always at your origin, and it always spaces down the two set of axes. What you're doing when you move the camera is really moving what you're looking at to in front of the camera, rather than moving the camera to where you are. That's how the transformation works. So it's sort of setting a view matrix, is really setting an inverse matrix to move the world to where you want to line it, and you can see it. Say that's common as a quantitative graphical programming notes. Now, having got your 3D environment in the right place to sort of organize, so view this environment camera, we need to go from 3-dimensional world coordinates into 2-dimensional coordinates. And we're going to use a projection that creates a perspective. So things that are nearer to the camera will seem bigger, relatively, and things that are further away will seem smaller, so it's kind of like the really world. If we have the camera at C here, we've got something called a view frustum, which is like a truncated curtain. You have the field of view of the camera but you have a clipping plane at the front and one at the far end. Now, we don't really care too much in this library about far clip. I don't bother with it. But the near clip's really important because you get numerical elements that you allow coordinates to come front near the camera. What we're going to do to make a perspective projection is to divide by the distance away from the camera. And as that distance gets smaller and smaller, then your coordinates get bigger and bigger. And eventually you then end up with a overclaim or possibly that divide by zero, which equals the point. Now, the maths library supplies a make a perspective matrix function, and you give it a field of view in the y direction, and obviously the bigger your field of view is, the closer, the more perspective is, the closer you are to the logic. We get more of a telephoto effect. If you go for a smaller field of view, then you can get as big zoom you see, so you start performing that way. You supply the aspect ratio. So let's say my Flutter canvas is 920 by 1080. And that's 920 or 1080 for the aspect. And you supply near the far plane in the world coordinates. Those are very complement associated in distance and time. In this library, it doesn't really matter too much on either or near a far plane. In a graphics library that would be rendered by the GPU, that's quite important when you don't use a bigger distance between near and far than you need to be your scene because of our precision problems or do with the same. But we're using plates, double precision plates here. You don't have to worry about the precision missions. So let's say your near clip is, for the it's about, let's see, it's about 100 meters from the camera. I have 1 meter, it's 1 minute. What the perspective projection does is creates these this cube of coordinates called clip coordinates. So you turn your frustum, which is narrow at one end and wide at the other end, into a cube, and you can see that the near piece has stretched everything. So these are the bit of the camera got bigger, and it's because the wide got smaller. And as a bit of a trick, the clip coordinates, for whatever reason, are left-handed rather than right-handed. So remember we said that X, Y, Z is coming out towards the viewer, and clip coordinates, they've got X and Y, and Z is going away from the viewer. So I suppose you're thinking about distance, where the camera increasing in clip coordinates. The reason I call it clip coordinates is because once you get to this point, it's easy to throw away geometry you're not going to render. Everything that's outside this cube, you're not going to see on the screen. So the whole sprite, if it's completely auto to the left, you can just throw away, throw away that again. We'll never drill. There's a further step to get down to what called normalized device coordinates, where this time the cube is just between -1 from one side. And the reason that the clip coordinates don't have that dimension is because you're trying to avoid doing a lot of divisions of the coordinates to get down to that. So the clip coordinates have a cube of sign W, minus W, W, and that depends on the projection. That depends on where you are and your shading to protection. But normalized device coordinates gets into something you can then turn into be coordinates you're going to use on the cards at the campus, which is the nearity with, I believe, you the front of my team today. So, right, last one. You just got your unit cube of normalized device coordinates. It's simple calculation to basically move everything so that the canvas, the origin is set of that coordinate. So you need to make sure that it is in the right place. With that NDC coordinates, the origin is bang in the middle, and the coordinates there for the -1 to 1. So we just need to rescan the things from the right place again. In the window. Okay, so that piece on transformations to get your world corners onto the screen is quite common amongst other graphic designers. Gel, plus GNU, do the same thing, So if you kind of get head around that, that's portable knowledge that you can use in other graphic systems. This is where we're going to go a little bit off piece and kind of do something a little bit different to what Klein or Reddings did. So the primitive in our graphic display is going to be a line, and we've got this on the left here. You can see we just draw a cube, and we don't make any effort to eliminate any lines that we can see, we can see that we get something that's a little bit hard to understand. You can't really tell what the orientation of tube is, and flip-flops are clearly two orientations. But as soon as we hide the surfaces that you can see, then you get a much better, much clearer image and understand seeing much more what the actual scene is. So conceptually, we are clipping every edge in the sea with every face. That's called our which sounds really expensive. That's like M squared. You should imagine GOG and faces and all that and edges. Now, mathematically, you can't really better than that. But what we'll see is that we could put some optimizations in to give us a much faster performance in that worse it is. Okay. Let's just have a little quick look at what human Birmingham does for you. So this is a screenshot from Star Wars in the arcades, at a vector game. Obviously, we have to stay on the master, but in the arcade cabinets, this was CRT in vector mind, or really, really master spec. Now, the mechanism can't do the in-service rule. It's just a small simple view. It can draw the lines, it can do perspective, and it can do like we're flying down a trench from Death Star, but it can't do the hidden substance. So I kind of just it's placed by hand, and you can see it's totally different. This you have a much clearer idea of what's seen there in front of you. Okay, so how are we going to organize in Dart our data structures? And at a really whole level, each of these objects is class in the right. So it's hierarchy. You have how you want scene in your current frame. Scene has a collection of sprites. Sprite is a bunch of meshes that are generally quite close together. Each mesh is composed of faces, and faces are about a matrix of edges and border, and the edge has two vertices. So for our vertex objects, we keep the idea of the same point in all spaces. So you'll get the 3D world vertex, and you can transform it into a Morgan transformation to where it's supposed to be from the origin point. We're going to transform it to the camera viewpoint, so there were two different camera, and then you go to normalized coordinates, so you clip it, and because last transformation is the default transformation, so you actually see it like place from Flutter and canvas. Edges, there are always straight lines catching two vertices, so we know that the perspective transformation distorts the scene, but edges always remain straight. It's not like a fisheye lens where you can have curved edges that were straight in the middle world. But this transformation, for any of the two-dimensional view, but it's always a straight line connecting to the vertices. Now, if the edge is part of a solid mesh, it must be connected to two faces. You can't have it solid any other way, and have it still be real in the world. And we have a flag for visibility, so this would be a good variant for the edge. And so the visible edge is you always attempt to draw it. It might be occluded by another mesh, but you always try and draw it. If an edge is invisible, you would never take space in. It never takes part of visibility calculations. It's always drawn. So sometimes we're drawing meshes together and we don't want the joins to appear, so we'll make that egg there to the visible. And we can have an edge that only appears on the silhouette. So if you have an edge that is part of two faces, but one of those faces is visible because it is back facing, then you know that edge is on the outline, the shape. And for example, a cone here, and you can sort of imagine a curve like this. If you don't draw the material edges in, you kind of have just the base and the curved top to it. Maybe. It's cheap, I'm not saying otherwise. A face is a collection of bases, but has a base on most. We say they're single-sided, so we will only ever draw the face from one side. If it's facing where we like for it, this means to clear forward, calling it out thin. It has to be flat, otherwise they're rendering defects. When it's about to see them, we'll face edge on, and it's not flat for the comment the render. It won't crack or anything, but some lines should be obscured lately, and some lines are obscured shouldn't be. The vertices on the ice, the edges are ordered. We need that later on to figure out which four round faces. And we had to have convex faces. You can't have any conhabitants in the mesh, within the base. So what we'll see later on is that the meshes are also convex, and the convex mesh never have a convex face. So when you do the transformation into screen space, any any face that is visible must have an anti-clockwise forward-winding the vertices. Can't be the other way, because if it was clockwise, it would have been tipped its face away from camera to redirection here. Right. So a mesh is a convex collection of faces. We made quite a good optimization by just having convex meshes. And if you wanted to create a shape that appears to be concave, we need to use multiple convex meshes to make that ever happen. I suggest checking out the Wikipedia page for 2D manifolded cylinders. You can't have anything complicated. No holes, no self-intersections, nothing other than a simple convex shape or mesh. And like we say, in a solid, it has to enclose space. You can't have any holes. Every edge has to have two base chains. There is an exception that if you'd like to model a single line or a set of lines that aren't on your face, say you're doing a car and you want the hair along with, and you don't want to make a bunch of meshes, you just want to have one line as a man of kind of arrow. You can do that, and the seam lines are fine in the calculation. They don't include them, I think, but they can be included by races, so they'll work. Okay. Yes, so like I was saying, if you look at this L-shaped mesh, what can happen is that from some angles, the concave face A can include some of the vertices in face B. So what this means is if we were to run our concavity, you would have to check each mesh for intersections with itself, and you have to check for including them with itself. And if we say that actually you only have a convex mesh, then we don't have to do that. Saves us a ton of processing. We can make more complicated shapes up from collections of convex meshes. Actually, it helps with modeling as well, because we can declare a certain weights. Then many convex hull below fronts, and that's the mesh, and have to specify each and all that individual, and makes things a lot quicker. Right, a sprite is like there's a phrase shit is a collection of meshes. And ideally, they would be doing up pretty like close. It doesn't help the however, when you say you made a sprite out of seven things, there were long-made items, so it would cause some calculation issues. The point about sprites is that all the meshes in the sprite have the same origin. So they're transformed as well. Since you can't have concave meshes, you need to sometimes compile your sprites out of convex meshes, so this transform the old objects of the whole unpayable. See example then, but yeah, fine. To help with testing, we generally don't want to transport all the coordinates of the sprites and meshes unless we help them. So at the beginning of the round that we made, the bounding box, AABB is an axis-aligned bounding box. It just means that it's extending from an X1 and Z axis that bounds the raw sprite. What we would do is we would cast one of those first, and then if the bounds of the sprite aren't in view volume, we know we're going to discard the whole sprite. And we've only done the work insertions for the maybe 50 vertices with a slide. We normally found 8 stages all over us too. And for translucency, we have a flag to say the sprite is translucent. It just means that none of its faces will include anything behind it. So you just see the sprite outline and kind of solvers that's behind what, like I say, it's cheating. Collision testing, as a result of collision testing to figure out what's behind, what's in front, and what these discard, we almost get collision checks for free because we're basically doing the comparisons, see what's overlap, what's colliding. And the library reports back on a sprite basis on which sprites collide with which other sprite. And at the top level, you have scene, and you basically take the scene object, you add your sprites to it, and the scene manages that. So in the old days, we would call this retain mode. This is where you don't have to keep on firing triangles that are in the more primitives that are the graphics library every frame. When you do the word VJL, you would always feed you triangles, which is sometimes called read mode. So what I'm offering is a system that manages your sprites for you and moves around. But if you don't do anything, you've seen you resplaying with people as some campaign. In order to create the sprite game, I wrote a little model in Flutter, really simple. And what you can see here is the player's ship. Every mesh is different color. So each of these classes are random convex mesh. And all work together in either in complex object and or we allowed it to still run one mesh. Right, we're getting towards the sort of the important bit. Promise this got too much longer. We've got 10 slides to say what we do with every frame. So Flutter comes up to us and says, right, here's your frame start, and we've got about 10 milliseconds to create a scene that has everything and quitting ball and cows. So first step is to throw away any sprite that doesn't end up appearing in the node, but we're not going to see it. So instead of doing it later, like like saying test out the mock system, you can see it, but go out to the UME. Very what's the secular test. Take the sprites flavor racks can be, then we break it down into rich meshes, and we do the same thing to each mesh and see which layers ahead are it. I'm not doing use called orbits. I do a region pack as a table. If a mesh overlaps the front chip plane from the airplane, then I throw it away completely. So the only way to deal with that otherwise is to make some new geometry that will reflect that mesh class against the chip plane. So you throw away the vertices that on this upper chip, and you have to make some, you have to join the face up base to build it and to still be solid body. That's just pain net. So I just proved like for that game that we've got here, it's really easy because nothing ever comes there, some camera all in this board. Right, so top 3 different things, 2 dimensions. What we can do now, have bounding boxes, we can find which sprites play with other sprites, and we just explore them as they explore them as this and sprite the two. We can eliminate a lot of comparisons doing this straight away, because clearly the 2 sprites don't overlap. None of their edges or these places can overlap. We don't have to worry about a test of visibility. We do the same for the mesh tool sprites. So 2 sprites overlap, we'll also check to see if any of their meshes overlap, and we add a list of each mesh with any of meshes and likes nothing like that. We can, like I was saying earlier, we can throw away approximately half the scene we've got on this stage, because the face away camera, we're never going to see it. Doesn't take part in any calculation at all, just discard it. So with these 2 cubes, they have 6 pages each, but actually only 3 of them mean to go to reach the next phase version, because you can't see built here. Now, you can do this by finding out the order of vertices as they're then on screen. That's a cheaper way to find out the way these creations for watching. In this case, they'll be anti-wires all the way, and the worst thing here at Alpha is minus a couple of things that end up. Because when I need to make the plane equation of the face the same later on, what I do is I create a normal vector. So I do a cross product of 2 edges in each face. I make a normal vector, and I test to see if the normal vector is greater than 90 degrees to the vector to the camera, in which case it's a delay of and the video. So in that way, we can then decide to wear a that is trace in way. But the plane we're playing, nx plus by plus cz plus d equals 0. If you have point in the face, and that's what A and C is. A and C families. The distance of the face and the origin is indeed man, and when you can make A by years, I can Now, to do part of the occlusion test, we need to know what the silhouette of a mesh is from the angle that we're looking at it at this particular point in the random process. So here we've got a cube, and you can see the rule problem and get rid of 3 edges because they're not part of the silhouette. Same test as before. If an edge is part of a face that is visible and its other base is invisible, then not one silhouette, and we can tag with as such. Okay, so quick detour. There's a chap called Arthur Acker who worked for IBM in the 60s. He was a RAX researcher. And his team published a paper in 67 about quantitative invisibility, a way to say how lines were shown or hidden in a scene. Now, what he said was, if a line was visible, a line segment visible through a quantitative invisibility of 0, and that would be sent to display list and we'll draw it. If the line goes behind a mesh, then we increase its quantitative invisibility by 1. It's non-zero, that part of the line segment never gets drawn, it always stays invisible. And then line out the other side of the mesh, then we reduce its quantitative invisibility by 1, and 0 it's back to invisible again. But imagine in a scene, you could be stacking 10 or 20 meshes in front of the eye, and the quantitative invisibility goes up, to perhaps 20 or whatever. And all those line segments have a QI rating of 0, and then we got to render those because they didn't hit by meshes. What we need to do is figure out how to find this QI value, and remember this is happening in real time in every plane, but every edge. Now, because we have a boundary of the edges in the silhouette of a mesh, we know that if we do a cross product, basically and check the sign, we can tell whether a line is going behind a mesh, so we have to increase quantitative invisibility, or just coming out from behind the mesh, in which case it will induce them. And the way you do that is, as I say, to cross product sign, that tells you which does casing on the tree. Right, back to the render. What we need to do to draw an edge on the screen is to look at the one end of first vertex, figure out what QI is from that, and then we go through like kind of intersections of the silhouettes of meshes. You can see it. And as we go over the line, we update QI depending on whether we're going from the mesh to behind. And anything after done all that, where any line segments were quantitative visibility from 0, we can send those to the display list and we'll blow up on the screen and then we'll pray. Again, so how do we decide how many meshes are in front of the start of the line? How do we get that initial quantitative visibility back? There's a few tests perhaps to apply. So here we've got 4 points, A, B, C, D. First test, imagine we've got our mesh on boundary box in screen space. So if we test a point as a bounding box, if it's outside the bounding box, then clearly we can't be obscured by this mesh. So void hanging label QI is not about at 0. But void B is inside the bounding box, so we need to test over to see a bit obscured by the mesh. And for that, we need to look at the silhouette, and there's a property called the 1D number that you can calculate to see if pointing to the side, followed up. Maybe we don't really have time for that at the moment, but let's assume that we have to use beat outside the silhouette, so we don't have to worry about adding consequent deal. We'll see that on. For C, it's past the bounding box test. It's inside the silhouette. So how are we going to decide whether C is obscured by the mesh or not? Now, in our screen space coordinates, we actually kept the Z coordinate. So we have a way of deciding if somebody is from new point, another is geometry. And remember, so we would create the plane equation in every case in every visible face in a mesh. What you can do is you can put the coordinates of C into the plane equation for each of the faces in the mesh. And if it's negative, you find that it is on the inside, T positive is on the outside. Something that is playback is on the inside, and how do singing invisible case is obscured by fan mesh and binding. There's even one service that is on the outside of then you install crystals in line there and say like the C200 stream by this mesh, and again, we might increase the content. And so the deal really is after their failure test and hardened. The only other bit of maths that we need is in 2 dimensions to decide if 2 lines are crossing. So imagine you have an image that we are trying to render on a bunch of silhouettes. Is it crossing the silhouette line? And it's just a bit of bookwork. If you check bounding boxes are left, then that means we have to check to see if they're parallel. So we can do one parallel. But otherwise, if you apply this formula, and what happens is you get the value between 0 or 1 for the transfer line, or then we're working what you're actually intersecting in the line, but what if outside the line. It's been actuated into 1 and you go to the line, so and say it's just right. So last bit after all that, we can hopefully have all the line that had a quantitative and a relative 0 are now in the display list. And what I've done to try and get the rendering thing as fast as possible is to make a display list like 42 months. So we have to allocate that in timing. And just let's say we're having a limit of 50,000 lines. So I'm going to allow 200,000 values of my for list sampling and wait for start the line. Sorry. At X and Y, start the line, and X and Y, and then, like I say, 4 values per 9. And if we call canvas tall wall points, it'll flip that box. It's pretty fast. It's not quite the endless boring because we actually maintain quite a to this every color. So you have a paint that queries will draw, but you have that in variants, all lines, or so none for the how to need to climb different displays with different colors. Okay, so 2 more slides and then I'm done. I really like the whole rected end. I think the work was pretty cool, and I'll really like that style. But I think it's very good. So it's like a technology that was really good at the time of low resolution raster displays, but everything's excellent nowadays. You can do some fantastic stuff, whether it's kind of Nintendo's kind of cartoony style, or Master Arts, the most realistic, playing really low, or get some nice practice. I think you can't really bring that back together to this shame. There are some problems with powering them, although using bounding boxes to get all the content is a lot better in most cases than n squares. The fact of the matter is, if you get a lot of things that will spikes towards off each other, the calculation slows right down and loads from first. And you could probably imagine this code is basically all if statements. Your relation testing is something in front of something else, is this line intersect and that kind of thing. But there's news. And you basically on a modern CPU, a froth, because you just see it up rather than so is there other stuff things like that. Yeah, so probably should be way down what the calculation. And finally, it's depressing, but we kind of live in what some people call an intention economy, and you need to show us up for the screenshot on Twitter, or we don't see it, and Twitter just basically makes a massive mess, and if they're really weird and just had it in mind, it doesn't impress very hard. It's really hard to get good at screen video that works on one devices when most teams are having a screen. So it's going to but if you do like vector graphics, modern hardware is just strain. You can still live your dream and have great visuals if you like that kind of stuff. Doesn't see anybody else. Yeah, that's kind of it's kind of what I read. Thanks so much for that. You got M&O.